minute, we'll see. Those things, and how did I start that sentence? It's been a long morning. I don't know where I was going with that, but I'll come back to it. I'll come back. It's in the same vicinity of what I've been talking about. What was I trying to say? I digressed to be approved. Too much digression. Lost the thread. But we'll be seeing it, whatever it was. Okay. So you've got this picture, you've got that question. I'll be asking you some questions about other transformations, okay? But nothing any harder to do than any of this. And then I'll figure out something really impossible just to keep you honest. Ask you to figure out something. Okay. You know what a vector space is, or you're getting the idea. You don't have all the axioms, okay? A subspace, as I mentioned, is just a vector space within a vector space, okay? So this plane in R3 that is your row space is itself a vector space. If you had any two vectors in that plane, you're going to get a vector in that plane. Zero vectors there, the inverse of any vector, there's always a vector opposite that's in the plane, it gives you zero. All the axioms, okay, all the properties of vector spaces. So to prove something is a subspace, all you have to do is prove that it's a vector space and that all the vectors in that space are in the space of which it's a subspace. Okay? So it's really not much different than what you've been proving. There are additional properties that I'll ask you to prove when we get, everybody has a textbook. Okay? So hopefully yours will be here next week. And but the other properties are generally even easier than the ones you were working with. Okay? The ones you're working with are kind of the most important ones. But there are cases of vector spaces where that doesn't work. Okay, where something else, there's some anomaly and one of the other properties just fails. Okay, because vector spaces can be very general. They're abstract mathematical constructs that can constitute vector spaces. They're pretty weird. You're not going to have to worry about in this course. Okay, everything you do here, your numbers are either going to be real numbers or complex numbers, or subsets of the real numbers. Maybe they're rationals. Okay, maybe they're the irrationals. There's the idea of span. Okay? The span of the rows here is just a set of all sums of multiples of those rows. So you take two vectors in R3, take the sum of all their multiples, well, you can visualize that as a plane. And that plane is the span of these two vectors. Okay? A set of vectors is said to be linearly independent if no vector in the set is in the span of the other vectors in the set. Okay? Which is equivalent to saying if you wrote down all the vectors as rows, the reduced matrix would not have any rows of zero. That's an easy connection to make. You're not going to understand it from my hand waving. Just giving you an idea. Okay? It's a simple idea, but you got to get some notation. Okay? Now let me give you one notation. That's going to be very important in this course. Oops. Well, I've been writing a lot today. I've had plenty of boards. Okay, but I can write the notation here. in general, if you want to write a 3 by 3 matrix, you write your first row A11, A12, A13. Your second row A21, A22, A33. So what do you think your third row would be?
A31, etc.
It's obvious. A31. A32, A33. Okay? So your first row, well, your row is indicated by the first subscript. Okay? So A75 would be in the 7th row. The second subscript is a column. Okay? So it'll be in the whatever number I said, column. Aij is in row I. Column J. Okay? Well, use that notation for any matrix. If it's bigger, well, you've got to have more columns or more rows or both. Okay? So it's pretty simple notation. So one thing I'm going to ask you to do is can you tell me what that's going to be? Oh. Yeah, I did it again. Okay. Now it works. I had started doing it again and look. WTF. What's this foolishness? Yeah. That's what it stands for, right? I keep seeing it all over the place. It must be what it stands for. Okay, so.
We can define it as what it means.
My definition.
It's better.
Yeah, you might want to be careful where you use it. Okay, now, anyhow, okay, you can write that out easily, okay? A11x1 plus A12x2 plus A13x3 and so forth. Okay? Well, we're going to use a summation notation for that. Okay, but I'm going to save that because you've seen summation. No, actually, I probably haven't seen a lot of summation notation. Okay? Yeah. Haven't had a course where you had to use it. You might have seen it elsewhere.
Just a tiny bit in pre-calculus.
Huh?
Just a little bit in pre-calculus.
Yeah. Well, we do sequence in series second semester. We do a little bit of it. Okay, but you haven't done enough of it to deal with this. It'd be a little more familiar to you than it is to Mark, but neither one was going to have any trouble with it. Okay? So, we'll probably go on with a little bit of sequence notation. I'll probably ask you to do a couple of problems involving these, although they're really a pain to type out. Okay? To make you appreciate why we want to do summation notation. Okay? It's just a notation that represents something obvious. But it looks weird until you sort it out. Okay?
Like this.
Yeah. Well, you've sorted it out, haven't you?